Good. So welcome everybody to another Earth to Class. I have a very brief introduction this time because this is one topic about which I know almost nothing. And going to have my friend Hung tell us most of what we're going to be learning today. Let me just see where my slideshow is. Okay, today we're going to learn about flood and drought in a part of the world that most of us know very little about, Afghanistan and Pakistan. These are not your local street flooding. These are floods which produce a tremendous amount of devastation in a part of the world that's not designed for devastation. As you see from these images, life is severely disrupted when the rains come. As I said, I suspect most of us know very little about Afghanistan and Pakistan, but they are located on a peninsula where Central Asia and Southeast Asia connect. And as this shows you, much of the area is mountainous. If you look at the scale on the side, we're going from 2,000 meters or about 6,000 feet up to over 18,000 feet. One of the main rivers is the Kabul River, which is shown here. And you get some sense of the water flow in Afghanistan. Many rivers, all of which are basically tributaries to the Indus River.
Mike, do I see that many of those have internal drainage?
Yes, a lot of internal drainage. A couple more pictures of the effect of the flooding. This was a flood from 2010. Give you an extent of what happens. Mountainous areas, but a lot of Pakistan is very flat. Okay, I'm going to stop my screen now and turn things over to Hung.
Thank you, Mike. So it's my turn to share my screen now.
Thank you.
Thank you, Mike, for having me here, and thank you everyone for attending. This is my second time with Earth to Class. The first time was around the same time last year. Last year I was talking about Southeast Asia, Thailand, China, Southeast and East Asia, and so this year I have expanded my research footprint a little bit further west. I'm going to talk a bit about Afghanistan and Pakistan. So for most of my talk, I will be focusing on what we have studied in the Kabul River Basin. And then I will, for the last few slides, I'm going to expand a little bit on a broader problem, the problem of having abrupt changes between floods and droughts. And that's not a problem that's experienced by not only Pakistan, but many countries. And as you probably remember, it's also a relevant problem here in the US, because in California, we have 2 decades of drought, and then we have an extremely wet year this year. So I hope this will be relevant to a broader context. Right, so let's get to the talk. So thank you, Mike, for the introduction. Mike has shown you a number of pictures of the floods on the ground, but I want to show you a bigger scale picture, the picture of the extent of the flood that spread through Pakistan, all along the Indus River Valley. Into that, this was a flood that happened last year, and it displaced 32 million people. The death toll was more than 1,700, and the economic loss was about 15.2 billion US dollars. And so this is a huge flood, and it came just 10 years after, just more than a decade after the last extreme flood, which was in 2010, which Mike also mentioned. So the future of Pakistan and Afghanistan, the future of the Indus River Basin is quite uncertain, because you have records flood in 2010, in 2022, and there are a lot of projections showing that extreme floods are going to get more extreme in the future under climate change. But there are also other projections showing that there is a warming and drying trends in the Indus because of global warming. So there are opposing trends being projected. In the Kabul River Basin itself, there is a projection of increased precipitation. So the projections are contradicting overall. It's also contradicting locally. Some regions is expected to be drier, some regions are expected to be wetter. So it's a very uncertain picture for the future in this region. And part of that uncertainty is because of the lack of data. We don't have a lot of, in a region with low political stability, it's very difficult to collect and maintain good amount of climate data to put into climate models and to study about what happened in the past and in the future and so on. But on top of that, there is also the problem of transboundary river conflict. The Kabul River, as Mike shown you earlier, flows from Afghanistan into Pakistan, and it flows through Kabul, which is the capital of Afghanistan. So to the Afghan people, it's a very important water source. And so there has been a lot of irrigations and dam projects being planned. This is even before the time of the Taliban. And little is known during the Taliban time and during the war, and now when they're back into power, what's happening in this region. But on the Afghanistan side, there are also many water resources, infrastructures being planned and being built. So there is a transboundary river conflict. And this is a region of not known for political stability. So the livelihood of the people in this region, it's gonna be very difficult given the future projections and given the current political situation. And I also have to acknowledge I didn't know very much about the region beforehand, and I also don't know much about now, but I happen to know Paolo Cherubini, who is a co-author on this paper. I met Paolo at a conference, and Paolo was advising Nasrullah, who is a Pakistani scientist at the time. And so through that connection, I get to work on this amazing data that I'm going to share to you today. And I'm going to be focusing on the Kabul, the headwater of the Kabul River. Now, my goal in this project is we have an uncertain future. So to make a better sense of the future, we look into the past. And the way we can look into the past is with three rings. I don't know if you remember, if you attended my talk from last year, but if you have attended E2C class regularly, you probably have heard about three rings numerous times. Basically, trees form an annual ring every year, almost every year. And by counting the rings, you know how old the tree is. And by measuring the width of the rings, you can infer about past climate, because tree growth is limited by temperature, moisture, and other environmental factors. So if you go to a region where tree growth is limited by precipitation, by moisture, and then you measure the growth ring, then you know that the big rings, such as this one, correspond to wet years, and the small ring, like these ones, correspond to dry year. And if you measure every single ring, and you do that for many, many trees in the site, and you do that for many sites in a region, then you have a pretty good picture of what the climate was in the region in the past. And you can go back several hundred years because trees live very long. And trees are an integral part of the water cycle because they record rainfall, they record soil moisture, and via that process, they can also tell you about snowpack, about the stable isotope content of the rainwater, and therefore they can tell you about the moisture source and so on. And so that's why trees are very cool, and I love studying trees. Okay, moving to the study area. This is the rain gauge that we are targeting. This is rain gauge is located in the Drought river, which is the Drought river is a tributary of the Kabul river. And so this is the boundary, the border with Afghanistan and Pakistan. If you follow the news, the Kunar province is where a lot of fighting took place during the last 2 decades. Luckily, we did not do anything there. We have a site that is right on the border between Nuristan and Kunar. And then we have 4 other sites on the Pakistan side. So we have 5 sites altogether, and we have 7. So from 2 of the sites, we have 2 different tree species. And so altogether, we have 7 records of past climate from this region. And we can use this record to reconstruct the amount of precipitation that occur here. So this region is kind of interesting because it's different from the rest of Pakistan. So if you look at the Indus River Valley, most of that is driven by the monsoon rain, which comes from the Indian Ocean. However, on the mountain over here, it's in a monsoon shadow. So if you look at the wind vector and the moisture transportation over here on the bottom right, you can see that in the monsoon season, most of that monsoon rain moisture go through India and go to the Indus River Valley, but it doesn't reach our side of here. In the off monsoon between February and April, this region actually receives moisture from the Mediterranean Sea. So that's kind of a unique part of Pakistan. Is very different from the rest of the country, which makes it also interesting. So let's build a tree ring time machine. For me, as I said, trees record past climate, and they are excellent time machines for us to travel back to time and look at what happened in the past. And this is the general landscape of that region. And this is my colleague Wahab collecting tree rings on the cliff, collecting tree sample on the cliff. This is my colleague Nasrullah, who is the first author of the paper. You notice that he's carrying ammo here. He is the only person who could go to Afghanistan and collect data because he has a cousin who lives across the border, and they belong to the same kind of tribe, and therefore he could go over. If I were to go over, I would be in danger. I'm very lucky to have known Nasrullah and have this collaboration. It's pretty dangerous work. So Nasrullah has been working on this site for a number of years. He actually started his PhD thesis with a site in Afghanistan and continue to collect more data in this region over the years. Now, with that 7 records of tree ring data that I showed you earlier, we were able to build a statistical model. It's actually a quite straightforward model. It's a linear regression that relates the amount of rain in the Kabul River to the width of ring growth. And so in this plot, I'm showing you the comparison of how well the model performed. So the black line is the observed rainfall at that site, and the blue line is the reconstruction, what the trees tell us. And you can see that the trees agree very well with the observation, and the model explains about 63% of the variance of the data, which means 63% of what's contained in the rainfall record is captured in the tree ring, and the rest is other factors that are not captured by tree rings. To a tree ring model, this is actually pretty good results. Sometimes you get an R square of less than 0.5, for example. So if you get 0.63, that's very encouraging. To show the quality of the treating work that Nasrullah has been working on. But you notice that there is still a bias between the triggering data and the instrument. So we do one additional step, which is called a bias correction. The reason being, if you look at the distribution of the reconstruction, which is the blue line, it's kind of narrow. It's narrower than what is captured in the instrumental record, because if you build a statistical model, it always doesn't capture the extreme. It captures the bulk of the distribution very well, but most of the time it doesn't capture the extreme. So we do something called a bias correction. Basically, we stretch the distribution out. This is called quantile matching. So we match the extreme ends of the reconstruction to the extreme ends of the observation. Basically, we stretch the blue line out to become the orange line, and therefore we have a little bit better estimate. So we have a model that works very well for the modern day, and if we use that model to extend the record back in time, then we have sorry, the keyboard keep flipping back and forth. If we expand that model back in time, then we have reconstruction. Now this is quite a busy plot, so I'm going to walk you through it slowly. Now the gray line is the reconstruction. It's a time series of precipitation in the region in the last 500 years. And yeah, so the gray line is the time series. The gray dots are actually just individual value connected by the lines. So if you remember, so recalling back the very first slide when I talk about the future of Afghanistan and Pakistan is uncertain. There are different projections. Some say it's going to be drier, some say it's going to be wetter. So we want to see what is the trend in the past, and that is probably helping us to make sense of what the trend is in the future. So the first thing we did, which is kind of similar to what everyone else is doing, is a simple trend analysis. So we just look at the mean or the median of the distribution, and so we see an upward trend. So it's precipitation increasing about 0.14 millimeter per year, but that trend is not significant, which means it's not distinguishable from random noise. Which, if you have a random noise, random data, it could also exhibit this kind of trend out of randomness. So this upward trend is not significant. But we are actually probably not interested in what's happening in the mean. We are probably more interested in what's happening in the extreme, because we are worrying about floods and worrying about drought. So it's not in a typical year, but what's happening in a wet year and a dry year. So we did something that is a little bit more advanced than typical trend analysis. We did something called quantile regression. So instead of regressing just the mean or the median of the distribution, we also do a regression with the extreme against time. And so now, this orange line here is the 5% quantile, which means the bottom 5% of the driest years. And then this red line is the bottom 1%, 1% of the 1% driest years. And then this is the 95%, this is 99%. So we look at the extreme end, the extreme dry, extreme wet year. And what we see is that similar to what's happening in the median, the wet years are increasing, but the trends are not significant, which means they're not distinguishable from random. However, the trend in the drying years are very significant, and the magnitudes are also bigger than what's happening in the wet year. This means that the dry years are getting drier. So, and you can see that clearly on the plot. If you just pick the driest years in every decade, you can see that they're getting drier and drier. So having drier years means having an increased risk of drought. So now, so let's try to quantify drought in this record. If we have the precipitation time series that we reconstruct earlier, and now we define a drought event is a sequence of years that started with 2 dry years in a row, because we want to avoid just a single dip, basically. And then we define a drought. What ends a drought? What ends a drought is a sequence of 2 wet years in a row. A wet year is a year with more than average precipitation, and a dry year is a year with less than average precipitation. And we have 2 wet years in a row, then we end that ends a drought, and that begins a period called a pluvial, basically a wet period. And if we have 2 years in a row, then that ends a pluvial and begins a drought. And so using that definition, we then have a record of drought events and also a record of pluvials. And here I'm highlighting the events that are longer than 10 years. So we have a lot more long droughts than long pluvial. That's the first thing to notice. And then if we plot all those droughts and droughts on to this plot, then we see a distribution of drought duration over time, right? So each of these bubble is a drought, and the color of the drought show how severe each drought is. The darker the color, the more severe the drought, and then the size of the drought correspond to the duration, and the duration is plotted on the y-axis. Now we can see that there is a clear downward trend of drought duration over time, which means that the droughts are getting shorter and they're becoming more frequent. So does that mean droughts are getting less severe? The risk of droughts are becoming lower? No, because remember, we're seeing that drought magnitudes have been increasing. So instead of having a few long droughts that we had before, now we have more frequent and shorter droughts. Now, if we have shorter droughts, does that mean we have longer pluvial? That's what we wanted to see next. And so we plot the pluvial time series, and curiously, we didn't see an increase in the length of the pluvial. So this plot is a similar plot to what you have seen earlier. The dots represent the pluvial, and the color representing the magnitude, and the size representing the duration. Now, we don't see an increase of pluvial duration. So droughts are getting shorter, but pluvials are not getting longer. Why? Why is that? And so I thought this was kind of interesting. The reason why we see this is because of the definition of droughts that we implement. Remember that we need 2 years of pluvial, 2 wet years in order to break a drought. So what happened earlier was that you don't often have 2 wet years in a row. You have several dry years and then a wet year, several dry years and a wet year, and that leads to the observation that you have longer droughts. And now those wet year pairs, the sequence of 2 wet years in a row, are happening more frequently. And so the fact that we observe that drought breaking wet year pairs of more frequent means that this is probably a manifestation of the wetting trend, which, because we see a wetting trend in the plot that I showed earlier, but it's not significant. So basically what I'm trying to argue here is that our statistical methods are not detecting an upward trend in the higher end of the distribution. It doesn't mean it's not happening. We're just not detecting it with this statistical test yet, but we detect it in a different way. We detect it in the sense of the frequency of drought breaking years of they're occurring more frequently, and that's why we have shorter and more frequent drought. So there is in some aspect there is a sign of the site getting wetter as well. So I hope that's a bit, that's not too confusing. I certainly find myself a bit dazzled at this at first. But if to make sense of that, basically what we should try to understand is that the water cycle is intensifying, and because of the intensifying water cycle, on one hand, one part of the water cycle is getting drier and the other part is getting wetter. Why? That's because as the atmosphere warms up, it's going to hold more water. So you get more evaporation. So the land and the soil and the rivers, everything is getting drier. But once all that evaporation that has been holding in the air falls down as rain, it's going to cause more heavy rain. And that's therefore the wet part of the water cycle is going to get wetter. The rainy part's getting more rainy, and the dry days are getting drier. That's basically the explanation. And what's the problem with that? The warning with that is that when we're in drought, we should not forget floods, and when we're in flood, we should not forget drought, because they're gonna change in between. So how do we deal with this conundrum? Maybe some of you are thinking about dams and reservoirs, right? Dams and reservoirs are designed to buffer ourselves against floods and droughts. They store water during wet years, and so that we can use during dry years. So reservoir is one way we can kind of attenuate the severity of extreme floods and drought. But we have to be careful, because reservoirs are not magical solution. So to demonstrate that, I'm going to temporarily move away from Pakistan and Afghanistan, and I'm going to Thailand to show you a very similar case study where there are two big reservoirs, and whether they could help with this kind of situation. So let's move briefly back to Thailand. Now, similar to Afghanistan, Thailand also experienced record flood recently, and that happened in 2011. This is the map of Thailand, and this is the map of the Chao Phraya River Basin, which is the biggest river basin in Thailand. And on this plot here, it shows the extent of the inundation in the 2011 Great Thailand Flood. All the blue areas here are the flooded area. So the inundated area is about 97,000 kilometers square. Can round it up to 100,000. It affects nearly every province of Thailand. The death toll is about 800 people. So this is about half of the death toll of the Pakistan flood. 2 million homes were destroyed. The economic loss is actually 3 times the loss in Pakistan, because of the economic value of land in Thailand. There's a lot more heavy industry, agriculture, tourism. There's a lot more economic activity in Thailand. So even though death toll is less, the flood extent is a bit smaller, but the economic loss is much higher. When the 2011 Thailand flood happened, a lot of questions were raised on the role of these two dams here. This is the Bhumipol Dam, the biggest dam in Thailand. The reservoir capacity is about 13 billion meter cube. You're probably more familiar with acre feet, but that's something I'm not familiar with. So, I'm gonna stick with kilometer cube for now. But for rough comparison, this reservoir is about 1/3 of the size of Lake Mead. Lake Mead is the biggest reservoir in America. So, and this is about 1/3 of the size. And then silicate is about 9 billion meter cube, so it's a bit smaller. It's about a quarter of Lake Mead in terms of volume. So these reservoirs are huge, but they did nothing or little thing. They did little to prevent the flood. The question was why? So let's see what happened during that year at these two reservoirs, and let's see what the role they could play. So this is the inflow, the time series here showing the inflow to the Bhumipol Reservoir in 2009, 2010, and 2011. So 2009 is the light blue, 2010 the dark blue, and 2011 is the red. And here is the same thing for the Sirikit Reservoir, 2009, 2010, 2011. So what happened was 2009 and 2010 were actually two dry years. They have two droughts. They have a short drought that happened in the 2 years prior to the flood. And then in 2011, what happened? 5 separate tropical storms hit Thailand and bringing torrential rain. Can the reservoir store these? Amount of rainfall? Now let's look at the reservoir operation during these 3 years. The reservoirs are designed to operate on something called the operating curve. So this is the storage volume and this is time. The reservoirs are meant to operate in between what's called the upper operating curve, upper rating curve, which is this line, and the lower rating curve, which is this line. And this is the same two curves for the Sirikit. So if the storage level is above the upper rating curve, they have to release everything to bring it down to below. And if it's lower, then they have to store it back to above. Now, then what happened in between, when the reservoir storage is in between these two curves, then they're gonna try to meet the hydropower and irrigation demand. So then in between these two curves is what we call the wiggle room, where they have the choice to operate. So what happened in 2009, 2010, as I mentioned earlier, these are two very dry years. The reservoirs were way below the lower rating curve, so they couldn't do anything. So in 2011, the operators were afraid of another drought. Sorry, I keep popping. The operators were afraid of another drought, so they start storing water as the inflow comes in. Instead of operating according to demand, they actually prioritize storing water. And by the time they realize that, oh, we are storing too much, it's already too late. When the flood hit in October, the reservoir were in excess. And by that time, the reservoir didn't do anything to mitigate the floods because they have been storing water instead of releasing it. So the reservoir could have played a role. The next question is, how big could the role could it be? It turns out that if the operators were aware were not being preoccupied by the previous drought, and if they a little more aggressive in releasing the water, they would have reduced the inundation area by 3,000 kilometers square. This is from a study from a modeling study that was published last year. So the total inundation area is about 100,000 kilometers square. So if they reduce by 3,000, it's only 3%. Not much. Not much in terms of absolute value, but if you consider the high density of the basin, if you just take a ballpark figure of 100 people per kilometer square, that would have been 300,000 people that you could have saved. Not in terms of life loss, but in terms of home damage and affected by flood and displacement and so on. So you could have saved 300,000 people, and among those 300,000, there could have been a few lives being saved. So the dams could have done something, not much in the grand scheme of things, but still we could have done something. So the lesson learned from that case is that dams are not the magic solution. They have a limit role, but even within that limitation, we still have to operate sensibly. The case of what happened here was that the operators were being preoccupied by drought and they did not operate optimally. They did not operate sensibly. And so that drives me back the message I was sending, that I was trying to make earlier. When in droughts, do not forget floods, and when in floods, do not forget droughts. And so if you remember earlier this year, a few reservoirs in California were releasing water. And there were a lot of questions. Why are the reservoirs releasing water? Why are they not storing water? Because we still in drought? Then you have to remember that we have a lot of snow, and so you have to preempt that. If you store water, if you are preoccupied by drought, you want to store water as much as possible, when all that snow in the Sierra melts, then the reservoir is going to be full. And then if there's a heavy rain event, or if there's a storm happen, you have nowhere to go, just like what happened in Thailand. So the conclusion for this talk is that floods and drought are two sides of the same coin, of precipitation extremes. And preoccupation with one side is dangerous. Again, you must always remember that after a flood, there will be a drought. And after a drought, there will be a flood. And so as the water cycle intensifies due to climate change, we should even be more wary of more abrupt swings between floods and droughts. And that's the lesson that is applicable not just to Pakistan, not just to Thailand, but to everywhere in the world, everywhere, even with or without dams. Yeah, so this is a very short talk. I hope that it has been useful for you. I kept it short so that we have a lot of time for questions. Thank you.
Thank you very much, Hung. One question I have for you is, do you see any connection between climate change and the precipitation changes?
Yes, so I don't do attribution studies personally, but I'm aware of several attribution studies that show the intensification of water cycle due to climate change. So Richard Seeger from Lamont actually have a very nice paper, pure theoretical paper showing physically what happens with when you have you can write differential equations and show that when there's more water, the circulation is going to be strengthened, and therefore it's going to bring more rain to the wet areas, and less rain is more moisture is taken away from the dry area, and so on. And for a lot of extreme events, there have been attribution studies that attribute that to how many percent of that to climate change and how many percent of that to natural variability. So yes, as the earth warms, we will see that more.
So are most of the floods from the precipitation or from runoff from the snows in the mountains?
For Thailand, it's definitely precipitation. For Pakistan, this particular flood was also from heavy monsoon rain and not from the mountain. The flood in 2022. Now, what's being projected for this region is that with global warming, you're gonna get more floods from stream flow as the glacier melts. But that's gonna happen in a short time frame. I can't remember whether it was 500 years or 200 years, but you're gonna get the increased discharge from glacial for a couple of centuries or so, and then eventually that's gonna dry up, and that makes sense.
It looks like Tom has a question. You want to unmute and ask your question, please, Tom?
Yes, I typed in my question. In Thailand in particular, I see a lot of rivers. So you only have the two reservoirs. Would just these two reservoirs have a major positive effect?
So let me go back to the map of Thailand. So there are, yes, you're right. There are a number of reservoirs in the Chao Phraya, but most of them are small. These are the two biggest. There's also one reservoir down here, and there's a lot of small reservoirs around the region. I have a map of all the reservoirs in Thailand, but I don't have it here. The effects of the other reservoir will be much smaller compared to these two. These are the biggest. And a number of reservoirs in Thailand are actually not on the Chao Phraya, but on the Mekong. So let me go to the map of Thailand. So this is the Chao Phraya. A lot of reservoirs in Thailand actually located on the eastern side. They are on a tributary of the Mekong. So they are different from the event that we are seeing here. Yeah, I don't know the extent of flood in the after 2011 flood in the other provinces, but here I'm just focusing particularly on the Chao Phraya.
Thank you. Ruben?
Is there any information about wildfires, and do you see increasing opportunity of wildfires that might indicate some aspect of climate change?
Okay, so wildfire is interesting. I'm aware of several studies of wildfire in Vietnam, so not in Thailand. So what we observe in Vietnam is that wildfire is the fire regime has shifted from one being driven by climate to one being driven by people. And so if you look at the fire frequency and the spread of fire in Vietnam, you see that before 1960s, fire were very frequent, but small incidents of fire here and there. If you look at and the occurrence of fire is strongly driven by ENSO, by the El Nino certain oscillation. After 1960s, then there's no relationship between fire and ENSO anymore. It's happening almost every year, and fire getting bigger, and we think that the reason of that is because it's now fire is due to human. As human live closer and closer to forests, as encroachment take place, basically we have more ignition sources, and yeah, that just spread fire in a different way than climates. So that's what happened in Vietnam. I don't know about what happening elsewhere. I don't study fire that much.
I have a question.
Yes, Jim.
Well, my sister lives in Arkansas, and on average, she'll see 3 to 4 tornadoes between January and April. So far this year, they've had 19. I look at some of the winds associated with some of these heavy rainstorms, and we've even seen them here in the Northeast. These monsoons that bring the rain, that's a quantity of water.
Yes.
How about the severity of the winds in those monsoons? Is it worldwide, or just part of what we're experiencing here in this country? I mean, in Arkansas, being a child of the 50s, we used to have bomb shelters, like that would help. They're installing these concrete bomb shelters as storm shelters.
Right.
And houses are no longer built with wood walls. They're using concrete blocks and breakaway roofs
Right.
because of the severity and number of tornadoes. And
Yeah.
I'm just wondering if that's also happening in Thailand and, Pakistan and, the severity of the winds that are bringing these rains when it rains.
So that's very interesting. I don't know anything about Arkansas or the Midwest or the Central US.
I'm just using it as an example.
Yeah. So the Asian monsoon itself has been on a weakening trend for the last several thousand years. This is just on a long long-term climate variability time scale. What we can expect with warming is that warming will reduce the land mass, the thermal contrast between land and sea, and the thermal land mass is what drives what drives the monsoon. So what we could expect is with that weakening thermal land mass, the strength of the wind will be weakened, but the volume is a different matter, right? Because the volume is controlled by vapor pressure deficit. That's how much the air can hold water, and that's
Right.
temperature. Yeah, so I think that's two different aspects that we have to consider both. And so, yeah, that's very interesting that you brought up. Thanks.
Thank you.
Any other questions? If not, I'd like to thank Hung for a very interesting talk.
Thank you. I'm very glad to be back to class another month for the second time. It's always been fun.
Okay, and I will be seeing you again next weekend,
Yes, thank you, Mike.
if not before.
Right. Okay, thank you, everyone.
Thank you.
Thank you.
Right.
Thank you.
We have one more Earth to Class this year, and we're also going to be back in the area of Southeast Asia. As Dr. Joachim Goes is going to talk about some of the plankton changes in the Arabian Sea. So I hope you'll join me on May 6th. And special welcome to those of you who are here for the first or second time. Hope you continue to come. And with that, please have a good weekend.
Thank
Tom,
you,
I
Mike.
hope you can go back to sleep.
Thank you,
tonight.
Mike.
Bye,
Thank you,
everyone.
everybody.
Take
Bye-bye.
care.
Thank you.